Hello students. In the last class we discussed some criteria for subgroups, and today we have to try to some specials of special subgroups. So first we have to just check is the intersection of a two subgroups is again a subgroup or not. So here we consider subgroups that are naturally arise with any group. Will explore how new subgroups can be derived from existing ones. The first one is the intersection of any two subgroups of a group G is also a group of G. So we have to use the criteria for showing that the subgroups. So we have to just check. First is we have to show that this take any two subgroups of a G, and then we have to show that the intersection of these two subgroups is non-empty, and then we have to try to show the is a closed or inverse also exist into the in this thing. So let us begin. Let H and K be any two subgroups of this group G. Then clearly H and K are as two subgroups. Then identity elements is belongs to G, and identity is also, so we have a clearly identity is the element of a H and identity is the element of a K. So if identity elements of a H and identity element of a K, then identity element of a H intersection K also. So we can say that if identity element of H and K also, that means at least identity element is belong to this intersection. So clearly intersection is non-empty. So we just say that E is the element of H and E, then intersection is clearly is a non-empty. Now we have to try show that in take any two elements A and B belongs to the H intersection K. Then clearly A and B are the element of H and A and B are the element of a K. So if A is the element of a and B are the element of H, then we can say that A B inverse is also the element of a H, and we can say that A B inverse also the element of a K. A B inverse is the element of H and B inverse are the element of a K. So A B inverse also the element of a H intersection K. And also because this is a satisfies this condition, so we can say that simply the H and since H and K are two subgroups, so if A and B are the element of H, and because H is a subgroup, so A B inverse is also belongs to the H. Similarly, A and B are the element of a K, and since K is again is a subgroup of a G, then A B inverse also belongs to K, and A B inverse is the element of H and A B inverse is the element of a K. That means we can say that intersection is also, because there are these two elements are common in the both, so A B inverse is the element of a H intersection K there. So we can say that hence H intersection K is a subgroup of the group G. We can extend this result for any subgroups, finite number of a subgroup of a G, and take intersection of this finite subgroups is again is a subgroup. So let's we try. Let I is a index of this, be a collection of all subgroups of a group G. Then intersection of Hi is also is a subgroup. Means we have to be assuming that H1, H2 and so on. This is a collections of subgroups, and then we take intersection of H1 intersection H2 intersection H3 and so on intersections for example Xn, Hn. They are also satisfy the condition. So by the this we can say that this intersection of all I, this is an index we can say that. So by the definition of intersection, H1 and H2 belongs to the intersection of Hi, implies that H1 and H2 are the elements of a Hi. So this means H1 and H2 are the elements. I is the index of this is the index set we can say, but clearly Hi is a subgroup of a G. If Hi is a subgroup of a G and H1, H2 are the element of Hi, then we can simply say that H1 H2 inverse is also the element of a H. So H1 and H2 also, H1 H2 inverse also belongs to the Hi for all I into this. So if H1 H2 is the element of Hi, then H1 H2 inverse is also belong to the intersection of a Hi. So it means we can say that intersection of Hi is a subgroup of G. So again, by the theorem we can say that when H1 H2 intersection, they are a non-empty, and clearly, because is clearly also is a non-empty, because this all HIs are the subgroups. So at least identity elements is belongs to the all of Hi, and then if identity element is belong to the Hi, then identity element is belong to the intersection of Hi. The Hi clearly is a non-empty. So this Hi is clearly is a non-empty, intersection of Hi is clearly is a non-empty, and also satisfy the second property of A and B are the element of this, then A B inverse is also belongs to the H. So we can say that intersection of any number of subgroups is again is a subgroup. Now is a naturally question arise, what we can say about the union of a two subgroups. If we have a H1 and H2, H and K are the two subgroups, and if what can we say that about the union of these two subgroup? Is the union of these two subgroup is again is a subgroup or not? So that is a answer. In general, we can say that union of two subgroups need not be a subgroup. For example, we just say that take a 2z under addition is a group, and 3z under addition is also is a group, and then these two are the subset of a z under addition. So 2z clearly 2z under addition is a subset of a z, and this is a subgroup of a z under addition. 3z under addition binary fraction is again is a subgroup of this. So this clearly these two we have to taking as a two subgroups of group z under addition. So now we have to take two elements, 2 and 3 are the element of a union of a 2z union 3z. But if we take, you can say take a 2 plus 3 is equal to 5, and 5 is 5 can be written 2 plus 3 is equal to 5, and then 5 is not the belongs to the union of a 2, because there is elements of a 0, 2, 4, and this is this elements of this 2z you have this clearly is a 0, 2, 4, 6 and so on, and the elements of a 3 is equal to you have a clearly is a 0, 3, 6, 9 and so on, and there is we have to take a union of this, that means clearly 5 is does not belong to the clearly the union of a 2z and 3z. So clearly this these two are 2z and 3z are the subgroups of z, and they are not closed under the binary operation addition. So clearly we can say that if it is not closed under the this binary operation, so they does not form a subgroup. So but naturally question is arise when we say that the union of a two subgroups are subgroups. So union of two subgroups of a subgroup is of a group G is a subgroup if and only if one of the subgroup one of them is contained in the other. So if either H containing K or K containing H is there. So if we have two subgroups and if one of them is containing the other, then we can say that the union of these two subgroups is again is a subgroup. Let us try to we have to prove this result. So the union of two subgroups of a group G is a subgroup if and only if one is contained the other. So let H and K be two subgroups of G such that one is contained the other, that is either H is containing K or K is containing in H. So thus H union K is equal to K or H union K is equal to H. So in this case you have H union K either K and H union K is either is equal to H. because H union K is equal to K and K is a subgroup of a G, so that is H union K is also a subgroup of a G. If we have a H union K is equal to H, then we can say that H is also is a H is already is a subgroup of a G, so union is again is a subgroup of a G. So in generally we can say that H union K is a subgroup of the given group of G is there. So I think this is clear. Now we have to clearly, if we have a in general union of a two subgroups is need not be a subgroup, but union of a two subgroup is subgroup only if one of them is contained to the other is this thing. Conversely, we have to prove this is a one part. We have H union K. If H union K is a subgroup, we can say one of them is a contain the other, then is a subgroup. Now we have to show that H is a subgroup, then we have to show that one of them. So conversely, assume that H union K is a subgroup, then we have to show that if the union is a subgroup, then either H containing K or K containing H. So we have to prove that H containing K or K. This means let suppose H is not containing in K, we have to go to the conversely. If H is not containing in K and K is not containing H, we are assuming that H is not containing K and K is not containing in H. So if not containing H, then there exists a element A and B. A is the element of H and A is not belongs to the K. Similarly, we have a B is the element of a K, but B does not belongs to H. So we have to be assuming that H is not containing in K and K is not containing in H. So if A is the element of H, then A is not the element of a K. If B is another element, B is the element of a K, but B we have to assume that does not belongs to H. So clearly A and B are the element of a H union K, and since H union K is a subgroup of a G, then A, B is also belongs to the H union K. So A is the element of H, B is the element of a K, A and B are the element of a H union K, and if A and B both are the element of a H union K, by the definition of because given condition is this H union K is a subgroup, so we have to say that AB belongs to the H union K. So if AB belongs to the H union K, hence AB is the element of a H or AB is the element of a K. So if AB is the element of H union K, then we clearly say that AB belongs to the H or AB belongs to the K. Case 1, if let AB belongs to the H. Now since A is the element of H, we have A inverse also belongs to the H. So thus we can say that A inverse AB is equal to, we have to just say that B, and thus B belongs to the H, which is a contradiction by 6. Because we have to say that B is the element of a K and B does not belongs to the H. So that means if A belongs to B, then A is the element of a H, H is a subgroup. So A inverse is also belongs to the H, then A inverse AB is equal to B, then V is a member of a H, which contradict the equation number 6, where this equation number 6 is saying that if B is the element of a K, then B does not belongs to the H. So case second, if AB is the element of a K and B is the element of a K and K is a subgroup, so again B inverse is the element of H, then A can be written in the form of AB B inverse, and this means this is the element of a K and this is also the element of a K, and K is a subgroup by the property of a subgroup. This under close property we can say that closeness, this is also the member of a K. So this is equal to A, and A is the element of the K, and we have to assuming that A is the element of H, but A does not belongs to K. But we have to show that A is the element of a K. If A is the element of a K, then means again we getting a contradiction to our first equation. So hence our assumption that H is not containing in K and K is not containing in H is a wrong. So what is the possibilities? Either H is containing K or K is containing H if you have a H union K is a subgroup of H. So we have to this complete the proof of this theorem. If we have a H and K are a two subgroups, then the union of these two subgroups is subgroup if and only if one of them is contained to the other is only possible. In general, we can say that the union of a two subgroup need not be a subgroup. Okay, so move to the next, we have to another definition is called is the center. So let the center of a group G we have denoted as a ZG is the set of those elements in G that commutes with every element in G. Means we have to collection of all the sets of this. G is the element of a G and G is commute every elements of a this capital G. Then we can say that is Gx is equal to Xg for all x belongs to G is there. The element of a G, Zg are said to be center in G. So the group is called is the center. This is G is called the center of a group. And now center of a group means we have to take a set of all those elements of G that commute with every elements in G. So this means we have to into this form. Okay, let's every abelian group is in Z. Suppose consider the group G is equal to set of integer under addition. Since G is abelian, because here is G clearly this is abelian, therefore every element of a G commute with all other elements, because already we have a giving the group is commutative abelian group. So we have a take any element of a this, we have to, because group commutativity condition, this is commute any other every other elements of a G. So hence the center of this is group is nothing but is equal to whole G. Zg is nothing equal to, we have to say that is a completely whole G. Now we have to try to find take a non-commutative group, and then you clearly know that the GL2R is we have to show that is a non-commutative group. Now we have to try to find the center of a this GL2R group. So we have to try to find what is the center of a this group GL2R. So we start with the to find the center of a GL2R, we need to determine all matrices A belongs to GL2R such that AB is equal to BA for all B belongs to GL2R. So we have to find such a matrix A belongs to the GLR where this matrix commutes with all the other matrices of a GL2R. This suppose for all B belongs to the GL2R. So assuming that A is equal to, we have taken a matrix A, B, C, D, where the condition is we have to, this is AD minus BC is not equal to 0 according to, because this is belongs to the, this is the member of a GL2R. So GL2R is a group where the all the collection of all invertible matrices, the determinant of A should be not equal to 0. So determinant of A not equal to 0 means this matrix we have a clearly AD minus BC should be not equal to 0, we have to just say that. So this we can say for A to be in the center of GL2R, it must be commute with another B we have to choosing belong to the is the element of a B. Another matrix we have to choosing this E, F, G, H is also, so here is we have to just say E, H minus G, F again not equal to 0, because this is belongs to the GL2R this thing. This means we have to for A to be the center of this GL2R, it must be commute with every B. This means, and then we have to this A, B, C, D, E, F, G, H all are the real numbers. So we need, this means that we have a AB is equal to B. So we have clearly AB is equal to BA. So we have to just try, we take a AB. So AB is equal to what? We have a take a product of these two, and then we have to complete A is into this form. So AE we have to take into this form, AEB G and AF this, and similarly we have a CE plus DG and CF plus DH. Now we have to calculate the BA, and we have to EA plus FB, and then we have EB plus FD, and we have a GA plus HC, and we have a GB plus HD. So the AB is equal to this and BA is equal to this. If A is in the center of a GL2R, then this condition is hold. Then these two matrix, these two AB and BA are the is the same. Is only same when this is equal to this. These two are the same, and then we have to say that similarly we have to say that all others are the same. So we have a thinking this thing. So if for A to commute with all B, the corresponding entries of AB and BA must be equal. So we have said the corresponding entries of these two are the same. This is corresponding entries of these are same. So these corresponding entries are the same, means we can say that AE plus BG is the same as this EA plus FB. Similarly, AF plus BH is equal to EB plus FD, and we have to similarly we can say that CE plus DG is equal to GA plus HG, and then we have to CF plus DH is equal to GB and HG is there. So is commute with all the B. This means we simply say that these corresponding entries of AB and BA must be equal. So this gives the following system of equation. We have these four system of equations we have. So now one by one we have to since these equations hold for all choices of E, F, G and H, so we analyze them. For example, we have to take this first one, AE BG is equal to EF, because it's true for all real numbers. So I choose E is equal to 1, F, G and H all is equal to 0. So if E is equal to 1, then clearly we getting A is equal to A, which is always true, and we have a B is also we have a 0. If A is equal to A, then we have a clearly what is the element of a B? B is equal to we have a 0 is there. So B is equal to 0. Now similarly we have to analyze another one. So another one is says AF plus BH is equal to C. Now choosing E is equal to 0, F is equal to 1, G is equal to we have a 0 and H is equal to 0. Then B is equal to 0, confirming that B is equal to 0 we have. Now third one we have to just checking in this form, CE plus DG plus GA plus HC, and then we have to choosing E is equal to 0, F is equal to 0, now G is equal to 1 and H is equal to 0. So now we have getting the C is equal to getting the C is equal to 0 from here. So we have a E is equal to 0, we have a G is equal to 0. So this means G is equal to 0. So we have H is equal to 0. So we have simply say that C is equal to 0 is the only possibility is there. Now last one is a CF plus DH, GB plus HC, and choosing E0, F0, G0 and H is equal to 1. Then D is equal to D, which is always true. So in general we have to showing that A is equal to A, B is equal to 0, C is equal to 0 and D is equal to D for the choices are there. So we have a B is equal to 0, C is equal to 0. The remaining entries A and D must be such a matrix A is equal to this thing. So we have a matrix is equal to B is such type of matrix A 0 and D 0, and clearly you just say that A and D we have to taking A D is not equal to 0. To commute with all other matrices in GL2R, for this is true, A must be equal to D. So this is true when this is A is equal to D. So if A is equal to D, we have A square, we have to clearly this determinant is of this matrix is equal to not equal to 0. So we have to just say that this is true, A must be equal to D. So consider therefore the center of a GL2R consists of all scalar matrices of the form lambda I, where lambda belongs to R and I is the 2 by 2 matrices. So Z of GL2R is equal to lambda I, and for lambda is equal to, this is the form of a lambda times 1001, and this lambda is equal to this thing. So the center of a GL2 is the set of all those scalar matrices there. So center means we have to, A is center of this matrix is like is this. This is the matrix which is the, if we multiplied any matrix, this is commute is giving to the commute the every other matrix of a GL2R. So this scalar matrix is the center of a this GL2R there. So now we have to show that the center of this okay, this is clear. Now we have to move to prove the one result, and that result is saying that the center of a group is a subgroup of a G. So center of a group of a subgroup of a G, we have to just say that because E is the element, we have a identity element is always belong to the center of a G, because it's commute every other element of this, because we have to EA is equal to A is equal to, we have a of E. For all A belongs to G is there. So it means if identity element belong to the ZG, that means clearly ZG is clearly is a non-empty. So we have to just say that this ZG is a non-empty. So since EG is equal to G, EG equal to G for all G, then E is the element of a G, and then we say that EG is clearly is a non-empty. So this means ZG is clearly non-empty. Now we have to take two different elements of a ZG and then say that they are commute. So let X and Y are the element of a ZG. Then for all G belongs to G, and we have we can say that this XY inverse, we have to show that this means XY inverse also belongs to the ZG. And XY inverse is also the inverse of G, means we have to show that XY inverse some G is equal to G times of XY inverse. So let us begin with the condition this. We have to start from the left hand side and then show that this right hand side is possible. This thing. So XY inverse G we have to write into the, because G X and Y are the element of a G, then this is commute with every element of a G. So X, Y inverse G, and G can be written as a GE, because we have not G of identity is equal to G, we have to. So this can be written as a G, and now we have to write as a E can be written as a Y into Y inverse, and this is again is the identity element. So in place of identity element we can write XY inverse G Y Y inverse, and we can say that YY inverse. So this can be written as a, because G is commute with X, Y is the element of this ZG, then Y is commute for every element of a G. So X inverse, this is commute by this. So Y G, and then this is Y inverse. And this YG, this means we have to using this condition associativity. Then Y inverse Y, we have again Y inverse Y is again we have a identity element. So this is X E G Y inverse, and you know that is X G Y inverse, because EG is equal to, we have a G. So we can say that we can also, this is equal to E of G. So EG also is equal to G, we can write into this form. So X G Y inverse, and then X is again the element of a ZG. So if X is the element of a ZG, means XG is equal to G of X. So we can say that G of XY inverse. So we show that, this means we can clearly show that XY inverse G is the same as a G of XY inverse. That means we can say that this implies that XY inverse is the element of a ZG. So we take two different elements, X and Y belongs to the ZG, and then we show that XY inverse is also the element of a ZG. clearly Zg is a non-empty, and we have to show that the this also closed into this form. So the criteria of this subgroup is satisfied. So we can say that means the center of a group G is a subgroup of G. The center of this is always is a subgroup of a given group G is there. Okay, now I have to stop here, and then we have to, in the next class, we have to continue some problems on a subgroups, and if time permit, we have to start the cyclic group is there in the next class. So I have to stop here for this today's. Thank you very much.